Hi everyone, I'm Manisha, PhD student here in mathematics. I'm going to talk about bathymetry reconstruction using observer. This is joint work with Vishal, Amit and DDA. This work is supported by IFCAM. So bathymetry detection. Bathymetry is a fancy word coming from Greek word bathos means deep and metron means measure. So let me tell you first in what context I'm going to talk about this bathymetry reconstruction. Its system is the water wave equation. Assumptions goes like this: the fluid is inviscid, irrotational, incompressible. Domain is periodic along x-axis, and the bottom boundary is time independent function, let's say zeta. The top surface is free surface, let's say eta. Phi is velocity potential, which means that grad of phi is the velocity at each point. So this is all in words. Let me tell you how we can formulate this mathematically. So this first equation is Euler equation, which is coming from incompressibility and in rotational. Second equation is basically says that fluid can't penetrate the bottom boundary, which means that normal velocity there is 0. The third equation is that normal velocity at free surface is equal to rate of change of displacement. And this fourth equation is Bernoulli principle, which says that pressure at free surface is equal to atmospheric pressure. Here, as I have already said, phi is velocity potential and small g is acceleration due to gravity. Notice here that the unknowns are phi and eta, which is velocity potential and free surface. So domain is unknown. So for our problem is given bottom boundary and initial condition for free surface and velocity potential, we need to find velocity potential and eta. So for our problem is known to be well posed. This is not of my interest. I want to talk about is inverse problem, which is bathymetry detection. So question is, can we recover the shape of bottom boundary given surface measurement? Mathematically, it means the surface measurement means given free surface. Can we detect the bottom boundary? Paper by Vishal and Junaid, they have shown that free surface at some time interval at equidistance points is sufficient set of measurement to detect the bottom boundary. Essentially, the idea used was harmonic continuation of phi given Dirichlet and Neumann condition at top to find out the bottom boundary. They had also shown that reconstruction is more stable in shallow water regime, which means that mathematically, which means that ratio of the depth to the direction length is very small. So let me talk about the second half of the title of my talk, which is observer. So definition of observer is, let's consider the very simple system, which is toppled OD initial value problem. So question is, given x, can we find y, which means that if we are given a part of the trajectory of the solution, can we find the trajectory? For that, we'll consider this asymptotic observer system, which is, you can say this exactly part is same as this with x as changes to x tilde, y to y tilde. And this is something called feedback term with where lambda is told the observer. Lambda here is a positive real constant. So the idea of this is that if we wait long enough, then x goes to x tilde, and then this system is exactly, this term is 0, and this system is exactly same as this system. Then y goes to y, y tilde goes to y. So now the point is, we want to make our system into this initial value problem, but which I had showed you was the boundary value problem. So let's try to get this initial value problem from there. Thanks to Zattarov and Redsulem, they had given this Hamiltonian equations for the water wave, where eta and q are canonical variables. Eta, as I have already said, that is free surface, and q is free surface potential, with the Hamiltonian given by this, where capital G is Dirichlet to Neumann operator. This is when given Laplace equation, given Dirichlet condition at top and Neumann condition at bottom. If we solve that and find Neumann condition at top, then this map from Dirichlet condition to Neumann condition at top is the Dirichlet-Neumann operator. It's a pseudo-differential operator. As I have already mentioned that this reconstruction is much more stable in shallow water regime. So let's just consider the shallow water model for this, which means is basically that we can replace this G with the GM. There is a systematic way to get this GM, which I can't out here right now because of the time constraints. So, and we can actually get infinitely such models. So correspondingly, we'll write the Hamiltonian and Hamiltonian equation. So then now this our system is suitable for the observer formulation. So let's go and see. This is the system. This is the system of interest, and we can correspondingly create the observer system. But notice the question was given free surface, can we detect the bottom boundary? But here, see, there is no, we can't detect zeta from here. Here, given eta, and if zeta was given, we could detect q, but not zeta. So this does not work. We need an equation for zeta. To get the equation for zeta, let's go to the definition of zeta, which was the zeta is the place where both the normal velocity is 0, means the fluid can't penetrate. That's the true bottom, which means that Neumann condition at bottom is 0. So in analogy to this Dirichlet to Neumann operator, we will define this another operator F, which is given Laplace equation with Dirichlet and Neumann condition at top. If we evaluate Neumann condition at bottom, that map from this given Dirichlet Neumann at top to Neumann condition at bottom is denoted by F. So as we had already said, this Neumann condition at bottom equals 0 solves the bottom boundary. It is the bottom boundary. In paper by Vishal and Detonate, they had solved this using the Newton method and found out the zeros and gets the bottom boundary. But what I want to do is we will consider the shallow water regime only initially, and then we'll do the, we can take the square of this so that it is positive and look for the minima. So to look for the minima, we'll look at the gradient. So finally, we have evolution of zeta equation, which is given by the gradient flow. Thus, we have our observer formulation for bathymetry reconstruction, where mu and nu are positive real constants. Now, if you notice that, again, as I had already said, that if we wait long enough, eta rose to eta tilde, and eta is evolving in this equation also. So this grad q to original q, and then hence zeta to the true zeta of our system. The only problem right now what I'm working on is to find out correct zeta and nu, so that we can get the attractor of the system, which is to say that we can actually get the solution of the original system. And this is sort of flow chart of my research work. My broad goal is to reconstruct bottom boundary with the better convergence and stability as they had in their paper, Vishal and Detonate. And the flowchart for this is, first we should construct this model equation systematically, and then we need to choose mu and lambda to guarantee convergence. Then also I would like to mention that this model equation I had just shown for one special dimension. We can do this for actually any special dimension, but physically only 2 dimensions are relevant. Now currently I am working on numerical experiments for this algorithm and its properties. Thank you for listening.
Any questions?
So I think in the second slide, you have just told that we need sufficient number of measurements. That's- I mean, sufficiently large means how much? I mean, TJ, yeah, J is 1 to N.
Eta at Tj for J for some, like, it should be just a time interval, and then at some time steps we need data.
Some means how many? Approximately minimum.
I
something
mean,
is there?
like, if you have around 500,000, that should be good enough.
It depends
Depending
the
on more
system
the
size
data we
or
have, more better answer. See, it's a ill-posed problem. We can't detect the bottom boundary exactly. So we are going to have in a small neighborhood of the bottom boundary. As much as data we have, better the approximation we get.
You need in time is essentially dictated by how accurately do you want to compute eta tt, and eta t, right? So that's really the issue. In principle, you can get away with a second order finite difference thing, but you will pay the price that it's only delta t squared accurate.
If there are no more questions, we would like to thank our speaker